Can you hear me? Yeah. Okay, good morning. Well, somebody's still arriving, but let us start without the computer now, because we had some problems. But we will try to solve this in the second hour. Well, I can see the lessons that you can also see in the web page of the school. And well, the first lesson is, to my mind, the most important. So I will start maybe slowly, but well, I think I think that then we can rush a little bit and then cover all the objectives. Well, the main objective of this lesson is to talk about. Excuse. This. Is to show you a mean-field-based method for studying nuclear structure at low energies, namely what is called the nuclear field theory. This nuclear field theory is kind of complete theory of how to treat the interplay between the single particle motion and the different collective dynamics of the nucleus. But it's also based on previous, let's say, empirical information. So it's kind of based in experiment theory, and at the same time it's a complete theory in the sense that eventually it's a method that we can use to get the exact result of the many-body problem. Of course, the idea of getting the exact many-body problem solution would imply to know exactly the interaction among the constituents, and this is another question. But when one uses this theory from a with some phenomenological input, it allows to understand in simple terms all or many aspects of the spectra in every kind of nucleus. And although I will focus on spherical nuclei, because when one goes to deform all this stuff, it gets somewhat more complicated, and probably we would need more days to do that. Okay, so as I told you, this is a mean-field-based theory, so we will assume, as usually, that nucleons move in some kind of central potential. As I told you, would be spherical, so would depend only on the distance to the center of the nucleus. And solving the Schrödinger equation in the standard way, we get both for protons, can get all the levels. And then filling, as usually, in the lowest levels, neutrons and protons, we get the ground state. Okay, so this is very standard. For example, this would be kind of carbon 12. Okay, 2 protons, 6 protons, 6 neutrons, and as far as we will have a even number of neutrons and protons, we will take this as a reference nucleus. Even better if this, as in the example here, fills some shell or at least some subshell. So I will be assuming that my reference nucleus, what I call the A system, is something similar to this example. Some levels occupied until some subshell is full. It could happen also that we prefer to study closed shell nuclei. But in principle, what I will tell about could be also applied to not fully closed shell, but a closed subshell system. Okay, so far this is our ground state, at least in the simple picture. And as I told you, we want to study the spectroscopy of nuclei, taking this as the reference system. What kind of excitations can we have here? Well, maybe you have already here in the previous lesson that one kind of very simple excitation we can have here is promoting from an occupied to an unoccupied level some of the protons or the neutrons. Okay, this basic excitation, we call it a particle hole. Okay, so we have particle holes that we will denote something like this, or we will also denote it as this, using second quantization could be another way of doing it, or sometimes you find in which you have hole operators, so the particle hole will be creating a particle, so the B would be the hole creation operators. Or you can also, and I will use it very much, use a kind of pictorial representation like this, in which I denote that I have now a particle above the Fermi energy. Let's say, suppose that this is the Fermi energy. So I have a particle above, and I denote it with an arrow up. And I also have a missing particle or a hole, and I denote it with an arrow down. I will use, well, mostly I will use this notation and this, but well, I suppose that you are familiar more or less with all of them. Okay, so this is a basic excitation with which we can construct, let's say, physical excited states. This is a particle hole. Of course, you can produce many different particle holes, promoting different neutrons or protons from different levels. So you have what I will call the particle hole basis. These particle hole bases are all possible particle holes you can construct starting from the ground state. Okay, in spherical nuclei, these particle holes should have good angular momentum. So usually all these particle holes would have some, what I will call lambda angular momentum, and parity also would be a good quantum number. For example, if you go to carbon 12 as here, remember this is the S1 half, this is the half, and there you have somewhere the D5 half. So, for example, promoting from a P3 half to a D5 half, you could create different couplings from 1 to 4 in angular momentum in this example. So if you have a particle like this and a hole like this, you can have all the possible couplings would be, as I told you, from 4, which is the difference when we make the difference, and these are the possible values of, and in this case the parity would be negative. So this particle hole would appear, negative. So this particle hole would appear in 4 of the bases that we can imagine in producing particle hole excitations. Instead, if you go from the S1 half to the D5 half, as a whole, and the D5 half again as a particle. So if you have this excitation, in this case you can go from 3 to 2, to 2, just to 2, because S1 half is only gives you just 2 possibilities, and in this case the parity would be positive. Okay, so we can produce positive, negative parity states of different angular momentum using the particle-Hall combinations. So suppose that we want to study some some excited state of carbon 12. If you go to the mass table or to the data table, nuclear data table, and you look at the spectra, you will find many different excitation of this kind. Note that it being even nucleus, this excitation contains integer angular momentum. Then we will go to other system and we will have half integer angular momentum. But for the even system, all these are integer lambdas. So suppose we want to study the 2+ excitations. Okay, so which, by the way, are the most important in many nuclei, the 2+, and the 3- would probably also could be said that they are the most important in our perspective. Suppose that you want to construct a physical state, a 2+, for example. Then, you can use the particle Hall, all the particle Halls coupled to 2+, and then try to construct a physical state, starting or using this basis, this particle Hall basis. Okay, in a naive picture or in a very simple terms, one would say, well, every particle Hall could be an excited state. So in principle, every particle Hall could be an excited state of the nucleus. But it happens that the picture based on the mean field is too simple. It's too simple because when you have a particle through the residual interaction, meaning the interaction that is not contained in the mean field, so all the interaction that is not fully implemented in the mean field, there will appear a matrix element. So they will interact among themselves. This matrix element, due to the fact that the central potential is not the full Hamiltonian, I will diagrammatically, or can be diagrammatically expressed like this. So if we have a particle Hall, you can have some matrix element due to the residual interaction that, of course, is this matrix element that, but diagrammatically can be represented in this way. Okay. We can call it the particle Hall prime matrix element. So all these particle Halls interact among themselves, so that we have now in this basis a Hamiltonian that has to be diagonalized, meaning that this interaction has to be taken into account. So in our Hamiltonian, we will have the particle Hall energies of our basis. We have many elements in our basis. But now we have to take into account that they interact among themselves. So we will have here one matrix element. Here we will have another one among the 1 and the 3rd particle Hall, and so on and so forth. Then, of course, we can fill all the rows. Here we will have the particle Hall number 2 interacting with particle Hall number 3, etc. We can construct this Hamiltonian matrix, taking into account all these matrix elements due to the residual interaction, and then diagonalize, or to solve the eigenvalue problem. Let me call this the different amplitudes on the different particle Halls by X. So we will have this eigenvector, and finally an eigenvalue that would be the energy of the more physical state. I mean, a state that has taken into account this interaction present in the nucleus. Okay. Pardon me? There are also some diagonal matrix elements in the residual interaction. Yeah, I don't want to. You should put it here also. Sorry. Some be here. 1, 1, 1, 2, 3, 3. Okay. And all this is Hermitian, so it's a symmetric matrix. Okay, so we diagonalize this with some numerical method, and of course, having taken from somewhere residual interaction, and we obtain from here the energy. We are supposed being calculating the 2 plus, so we will call it the energies of the 2 plus, and we have also the eigenvectors. We will have these eigenvectors from the diagonalization. Well, as you can imagine, and it is obvious, you will obtain many eigenvalues here. If your basis contains 20 particle holes, you will obtain 20 eigenvalues. In principle, the particle hole basis in practical calculation can be taken full, meaning that we can take so large particle hole basis that we converge. If you continue to adding more and more particle holes, you don't obtain any change in the physical states. So we say, and this is a nice point of kind of calculation, we can use full basis in this sense. Okay, so we will obtain many of solutions, so we will need another label to distinguish them. Maybe we can use another label that will distinguish all the eigenvalues and all the eigenvectors. Okay, with this eigenvector, I obtain a linear combination of particle holes that would be the physical state. And with it, I can calculate different observables. For example, I can calculate the probability of quadrupole transition from one of these states to the ground state. So I can calculate the quadrupole amplitude of the transition, and this is calculated very simply, making the superposition of all the particle holes according to their amplitudes in the physical state. So this would be something like this. Where here I will use the particle hole, the single particle hole matrix element. You will have to sum all particle holes, the 1, the 2, the 3, 4, etc. Each one contributing with some matrix element due to the quadrupole interaction. This basic ingredient is nothing but the usual matrix element due to the quadrupole field. This is the quadrupole operator. The charge, in principle, only the protons should contribute to the electric transitions, only the protons. So here, of course, I should multiply by the charge of the different particle holes. If the charge is 0, because it corresponds to some neutron jump, the contribution here would be 0. But if the amplitude corresponds to a proton, will give a contribution that can be calculated, as I was saying, through the quadrupole operator and using the particle hole wave functions coupled to 2 plus in the whole space. Okay, so with this basic particle hole transition amplitude, I construct the physical particle-Hall transition amplitude. Well, I will try, or as I told you, I will use very much diagrammatical representations. So let me give a diagrammatic representation of this calculation. So first, I will represent physical states, the ones that I obtain diagonalizing. I will represent them by a wavy line. The reason for using wavy line is historical one, because as we will see later, these states are very close to nuclear vibrations in some of the cases. So just for reminding this origin, historical origin, the solution of the diagonalization, it is represented by the wavy line. A wavy line having some good angular momentum and parity, in this case, the 2 plus. So this would be the transition, electric transition matrix element between these 2 plus and the ground state. This will be represented in this way. I want to go from the excited state, that is this wavy line, to the ground state, that is represented as the vacuum, through the operator, electric operator, quadrupole operator. Okay? And as you can see, this is obtained by summing on the different amplitudes at the particle-Hall level, using the eigenvector we obtained before. So this can be written by saying that this transition through the electric field is the one that I obtain by summing the contribution of the different particle-Halls through their amplitudes in the physical states. Okay? Of course, I'm talking about a very individual one of the many physical states I obtain. So I'm talking about the state number I, because I'm using the amplitudes of the state number I. Okay, so in this way I can construct and I can analyze the spectra of this reference A system. Of course, this is only a basic step, because then you can construct, and in principle you can think in superimposing 2 different physical states. For example, you have calculated some 2 pluses, you have calculated some 3 minus, performing the equivalent procedure, and then you can think in producing a combined excitation in the nucleus of the 2 plus and the 3 minus. Okay? And in this case, have many different possibilities. You have from 5 to 1, with with negative parity. Okay, and performing this, let's say, this little game of superimposing the basic particle-Hall-like excitation, you can construct some spectra to whatever energy, because if you add enough number of basic vibrations, you can construct even at high energy spectrum. Okay. Well, the method or the way of calculating things that I have just sketched is called the Tamm-Dankov approximation. Tamm-Dankov approximation, and is in the literature is very commonly written as TDA. It's an approximation, as it is obvious from the name, and it's very simple as a theory. Sorry. Okay. It's very simple as a theory. You see, it can be easily argued and written down, but it's not, let's say, good enough. It has a kind of intrinsic defect. What is this defect? Well, the basic defect or the intrinsic defect of Dankov approximation is that it does not fully solve the problem of the particle-whole particle. Be more explicit. We have written the Dankov approximation by saying, well, we want to take in all these processes, and from there we want to produce physical states and produce the spectra. But there is a particle-whole interaction, residual interaction, which is this one. This is also a particle-whole matrix element through the residual interaction. The point here is that it is connecting the ground state with a two-particle-to-whole configuration. One could say, well, I don't care because I'm not interested in studying the ground state. I'm interested in studying the excited states. So why should I take or be worried about this? Well, but you can easily think that if your ground state is not well defined or not well treated, of course the excitation that you make on this ground state will not be good enough. Well, this can be seen easily or immediately as in the following. This matrix element is telling us that in the physical ground state, write it like this, different. We're talking in the beginning. In the physical ground state, of course, ground state, mean field component, but we have some. This is a kind of a spontaneous appearance of a two-particle-to-whole in the original ground state due to residual interaction. Well, and this affects also the spectra you calculate. And this can be seen immediately. Suppose that you act on the ground state, on the physical ground state, just in the moment that the vacuum, that the original ground state has produced this fluctuation. And if you act exactly on this moment, at this time, you could produce a particle-whole excitation, which is what we wanted to treat before, not by creating a particle hole, but by destroying a particle hole. If you destroy this particle hole with a particle hole annihilator, something like this, if you want, you obtain a particle hole over the original ground state. Yeah. This and this.
Yes, visually I can see the difference, but I don't see this difference.
Well, this, if you want, particle, well, I wrote it before, no? You have the residual interaction, and due to this residual interaction, you have some matrix element, okay? What is this one? Well, this one is the one takes you from no particle hole at all, so from this ground state that we were saying in the beginning, so we will write down like an ket, and now the residual interaction will take you, which is a two-body interaction, okay? It's good that you made the question because it's important. It is being a two-body interaction, you can produce two particles and two holes. Pardon? Yeah, you can think in this direction like time. Okay, it's not real time because everything here is stationary in a way, but you could think, if it helps to think this as a time direction. So, being this a two-body interaction, well, you can have a scattering, because in reality, this matrix element here, the particle hole prime. Remember that a hole is nothing but a particle that was below the Fermi energy promoting. So this in reality is nothing but this. States occupied. Now, in the end, they are not occupied because they have to they have gone to the p and p prime configuration, single particle states. And as I was saying, the fact that in the ground state you have this possibility, so it will happen that everything that can happen happens. So you can have the possibility of creating a particle hole by destroying a particle hole, because in your ground state you have already components that are two particle to hole. Well, so a more general, and I would say a right one way of taking this possibility is by the operator that produces a physical state is not only that composed of creators of particle holes, but you must have in your operation creator of excited states also the you can write it like here with some amplitude. These are the so-called backward amplitudes. And this is a more general starting point for calculating the physical states. The wavy lines that, by the way, I will call them phonons, also because they remember the surface vibrations. Okay, the theory, the mathematical method needed to develop the theory or the consequences of this more general operator are the so-called random phase approximation. The random phase approximation is thus a more sophisticated particle hole treatment of the spectra in an even nucleus, but that contains, in a way, very similar concepts to the Tamm-Dankov approximation, but includes also these amplitudes, backward amplitudes, that may be important in many cases. In other cases are not so important, but in some cases are very important. In which sense they are important? They are important because when you calculate the quadrupole or octupole electric transitions, sometimes it's a systematic problem that Tamm-Dankov had. You were obtaining Tamm-Dankov low values, too low values when compared to experiment. When you perform RPA, systematically you obtain better results in this sense. So as a rule, the B is in the of the amplitude, I mean the intensity of multiple transitions in RPA, as a rule, are larger than in Tamm-Dankov. Well, not for every wavy line, but for the important ones. And let me now be more explicit. Important wavy lines. As I told you, I hope that later I will be able to show you some pictures. When you obtain all these different physical states, not all of them are kind of strong states, in the sense that many of them show very little electromagnetic transition probability. And this for us is important, because when constructing single particle basis, and when later we will go to the odd system, it will be important to keep the strong phonons. So if you represent, for example, in a quadrupole calculation, the B2s, a typical result, for example, if you go, I don't know, to carbon, to calcium 48, is that you obtain something about or below 5 MeV, maybe 2, 3 MeV. You obtain what is called the low line state, because it's the lowest in energy. Then you obtain many different, as I told you, you will obtain many different solutions. And then in a region about 2 times, in the case of the quadrupole, 2 times 41 8 to the 1 minus 1/3, namely the oscillator strength in the nucleus. About this energy, you obtain again a number of states showing an important B2 value. Even more, if you sum all this, you obtain a rather important set of states. Okay, this is called the low line, and this is called the giant resonance. You obtain this kind of result also with Tandankov, so you don't need to go to RPA to get the qualitative picture. But as I was telling you, when you go to Tandankov, to RPA, sorry, as a rule, the low line gets stronger in the RPA. Gets stronger. So if we plot here Tandankov and RPA, this would be RPA and Tandankov. Also, the energy can change, not only the strength, but also the energy. As a rule, and I should write it the other way around, as a rule, the RPA goes a little bit lower than the TDA. So we have both an increase in the strength and a small shift down in energy. The giant resonance gets also some differences from RPA to TDA, but the most evident differences appears for the low lines. Okay, we'll not develop mathematics because, as I told you, it will take us some extra time, and maybe if this we could discuss, it could be one of the things to be discussed. But just let me tell you structure, the final structure. The final structure of the RPA Hamiltonian, well, it's not really Hamiltonian, but the eigenvalue problem in the RPA is similar to the Tandankov, but is kind of more general. In the first block, we have the Tandankov matrix, which is this one, in which the other kind of matrix element appear. So here we will have the matrix elements that were not considered in the Tandankov. In the first block, we have this matrix, but with, ask me now why it's a opposite sign. This should take some discussion, as I told you. And here you obtain the same Tandankov matrix element with opposite. Well, this is the structure of the RPA eigenvalue problem. So here we have Tandankov, the new matrix elements, and with this structure again. And the different amplitudes appear for the Tandankov block exactly as we had before, and now we obtain the backward amplitudes. So this new eigenvalue problem, well, of course, will give rise to somewhat different energies and to somewhat different eigenvectors. And as I told you, this new will somewhat improve or make stronger the low-lying quadrupole transition. I told you that the Tandankov and RPA structure spectra is similar, low-lying, a giant resonance. Let me say just a few words of why this is the structure, because and what is exactly the meaning of this low-lying state. If you go to this basic formula for the electromagnetic transition, you see that in order to get a strong quadrupole transition, what you need is that all these different contributions, that can be 10, 20, or 30, depending on the size of your basis, what you need is that contribution, when you sum them, don't get summed randomly. If one is positive and the other is negative, and you start to sum positive and negative things, probably you will obtain something small. So, what is the meaning of having a strong quadrupole transition? Well, you obtain a strong quadrupole transition when there is a coherence, some kind of coherence, in the eigenvector amplitudes. A coherence that has to do with the matrix elements of the quadrupole operator. So a strong electromagnetic transition, quadrupole, for example, will appear if the particle Hall components of your physical states are proportional in the same, or have at least the same sign of the magnetic, of the electromagnetic matrix element. The sign. Okay. If you have this situation, well, you will obtain a strong superposition of all these sum, and in the end you will obtain a strong quadrupole amplitude and a strong transition matrix element. Okay. Well, this kind of coherence in the sign of the eigenvector is what is called collectivity. If you have a collective motion of the nucleons in the nucleus, they will give rise, as I try to explain later, rise to a coherent wave function in this sense, and it can be then understood that the strong intensities in quadrupole or octupole electric transition has to do with collectivity. Okay, this collectivity is stronger when you perform RPA, or is catch in a more efficient way by RPA. But in both of them, you can find this kind of collectivity or coherence in the wave functions. Okay, I don't know. You used to stop 10 minutes. Okay. Okay, so let me just finish this first hour then talking about the collectivity. How we deal with this concept and how we connect with the Tandankov and RPA formally. Okay, so now we change very much the language. Now we adopt what of the excitation. Until now we were thinking in protons, neutrons, jumping, And now we will think in another way. We will think that our original nucleus, the ground state, the one we take as a reference, is spherical, and that excitations of this system come through a deformation. So this very much reminds us the liquid drop model. So we have an excitation that will come from a deformation. This, according to the liquid drop model, oh, what a mess. I was in airplane mode. Sorry. Well, so according to the liquid drop model, any deformation, well, any, if we think that in a spherical nucleus, any deformation will lead to an excited energy. How we treat, or how can we describe a deformation? Well, there is a very simple way, by saying how is or where is the surface of the deformed system according to the different angles. In a spherical situation, the radius does not depend on the angle, of course. But if we get a deformed system, we will have, for example, if we think in a quadrupole deformation, something like this, where this would be kind of ellipsoidal deformation. So this is the harmonic spherical epsilon 20, and this would be the amplitude of the deformation. Of course, if this number is 0, we return to this situation, because everything would be independent of the angle. So the angle dependence is coming here. With this little mathematical expression, you obtain something like an ellipsoid, okay, which has quadrupole deformation, and by the way, has quadrupole moments of the electric quadrupole field. Okay, so if we had this kind of system, it could decay by a quadrupole transition to the ground state. Okay, but we are dealing not with a liquid drop in the real sense. It's not a drop of water. It's a nucleus. In a nucleus, you should consider that being a very small and microscopic system, we have to use quantum mechanics, and this parameter that in principle would oscillate so we could think in a liquid drop oscillating and eventually forming a transition to the ground state. If we consider, as I was saying, the system is quantal, this will lead expression of these amplitudes, as in the harmonic oscillator, in the standard harmonic oscillator, in terms of rising and operators. Maybe you remember, if you have the standard harmonic oscillator, you have the different states, and you have the rising operators, usually written in this way, and the lowering operators, leading you to smaller energies. And the X operator is usually written like this. Okay? This is a very standard harmonic oscillator in treatment in quantum mechanics, and here we can use the same thing. We can say that this classical oscillating parameter or degree of freedom, if we quantize or we take into account that this is system should be considered an operator with some 0 point amplitude, okay, and with some rising and lowering operators. If we are talking now about quadrupole states, we would have this rising and lowering operator, meaning that this amplitude, when you quantize, can be written in terms of creation of an excitation and annihilation of an excitation. Okay, this is then the quantization of a very pictorial or very intuitive way of treating the excitation in terms of the liquid drop of the collective. Well, but this this rising operator is the operator that creates an excitation of the system. So this rising operator can in principle be compared with that we obtained in RPA. Remind, or in Tandankov, this operator was constructed in terms of the amplitudes of the solution of the problem and the creation and annihilation if you were using operator. Now we are constructing in a completely different way the same kind of object, an object that is able to make transitions between the ground state or a quadrupole excited state. So this is the one in RPA. This is the one we are constructing here. Okay. Okay. So we should compare the two theories at this level. In this 0-point motion that we have in the formulation of the quanta oscillator, we have also the energy of the system, the energy of the quadrupole oscillation, and we also have the harmonic, I mean the restoring force strength in the oscillator. Okay. Well, you go from a time-dependent description in classical terms of a variable that just make oscillations to a quantization in exactly the same way that you do in the usual oscillator. Okay. So our operator. Our description of the system in terms of the liquid drop or the classical picture contains also the energy and some restoring force constant as we had in the usual. Well, if you are able to calculate these two numbers, well, you can compare with RPA, for example. Which are the energies that we obtain with this picture, which are the strength associated to the excitation operator. Well, let me say, how can we get the energy from this picture? The energy oscillation will be obtained by means of what is called the self-consistent condition. And it is obtained in a way that is similar to I would say, the old theory of the atom by Niels Bohr. You had some classical description, and then you try to fit with some quantum conditions. Okay, let me be more explicit here. If you have an oscillating, then we can say a classical oscillating system, you will have a classical oscillating surface, just because your parameters are oscillating harmonically. Okay? So if the surface is oscillating classically by now, the potential that the nucleons will feel will also oscillate, because the nucleons are inside the nucleus is getting deformed, so the potential that was spherical in the beginning, now it will also be deformed. So the nuclear potential is a spherical one. The nuclear potential here, of course, depends on the angle, as it happens with the density. Here is the essence of the cell consistence condition. So before we were just thinking in terms of the liquid drop, and so perhaps in terms of density. Now we have to think that also the potential associated with the nucleus get deformed in a similar way. So we have some kind of consistency between the description of the density and the potential. If you have potential that that depends on now the angle and varies with time, and if the deformation is small, so if this amplitude is small, you can treat this as a perturbation in the original potential. How you do that? Well, you do it in two ways. So we are saying that the formation is small, and we can do some kind of perturbative analysis of this problem. In which way? Well, the first one is that the potential, when it gets deformed, which in principle would have this expression, meaning that the potential in the new point is the potential on the original point in the spherical nucleus. If now we assume all deformation, this can be expanded. So this is a first approximation. You make a little, say, Taylor expansion here, and you obtain a minus, because this is in the denominator, and then you obtain the derivative of the potential. And then you obtain also this one. So for a small deformations, the deformed potential is just the original one plus a little perturbation. This one? Yeah, this comes from the fact that you can say where this point comes from here. It's just the inverse relation here. How to say? You got it? Good. Happy. Okay, well, if in case we can discuss it later, but in a way is this the idea that the new point comes from the original one through the inverse relation of the deformation. And if we have this expansion, assuming a small amplitude, well, we get this. And now, even more, we will add the fact that this amplitude is oscillating. So we already have a small term, a tiny dependent small term perturbing the original potential. Well, this problem can be solved by time-dependent perturbation theory. Okay. And, well, I should look, because these are too long equations and I cannot remember the details. You have this in the, if you have these notes, you can find what I will write down now in the very end of the notes. It's in the end of the second appendix, under the name of vibrational potential model. Okay, so what you obtain is using perturbation theory. You obtain a new state, a perturbed state. So it's the excited state, which in perturbation theory would be the usual expansion in terms of the ground state plus some components. Okay, some components, time-dependent amplitudes, that we want to express in terms of particle Hall, because this perturbation on the original ground state will produce particle Halls. Okay. This would be a time-dependent perturbation expansion for the excited state, and should be solved for this perturbation here. And well, you have to solve this amplitude. And when you have this amplitude, you can now solve, get the new density based on this amplitude. The new density will be the original one plus this amplitude that now contains the particle Hall excitations. And when you substitute what you obtained in perturbation theory, in time-dependent perturbation theory, you can see what kind of density you are obtaining through the time-dependent perturbation theory. Okay. And then you can ask yourself, this density I obtained through perturbation theory correspond to the density I was originally imagining? So is this equivalent to a density that was the original one plus some deformation? The deformation of the density can be obtained in a similar way by expansion, expanding the original density around the spherical. So this is the point of consistency. I want that the oscillations I was supposing in the density and affecting the potential will produce a density, like calculated through time-dependent perturbation theory, that is not in contradiction, or even more, is agrees with the density that is associated to the liquid drop model description. Okay, the answer, normally not. You don't obtain, if you put whatever frequency here, the thing is not, you don't obtain the same value. But sometimes, yes, in particular for some special values of omega, the answer is yes. So we are fitting a classical description in terms of a deformation and oscillating in time through the cosine. We are fitting a quantal description through the independent effect on the ground state. And this gives rise to some special values of the frequency and consequently of the energies. Well, this is nothing but saying that in this way, requiring this consistency, we are obtaining a discrete spectra for the vibrations. So in this sense, as I was saying in the beginning, this is similar, or although somewhat more complicated, than the original idea of Niels Bohr. Niels Bohr was supposing a classical orbitals around of the electrons around the nucleus, and imposing a consistency that in that case was the angular momentum quantization, or the de Broglie wavelength, was obtaining a special situation in which both things were matching. Exactly the same ideas is behind this way of thinking in the description we have just made. We suppose a classical motion, then we look to the quantal consequences of this classical motion, and if we want them to fit, we obtain a discrete set of values of omega. So we have quantized the spectra. Okay, I have not go into many of the details of this calculation, of course, but just let me write down, and then I finish now, write down which is the equation that is governing this discrete set of states, and this is the so-called dispersion relation, in which we have the particle holes coupled to the good angular momentum. We have the perturbation of the potential. Okay. Which connects with the ground state. And this matrix element goes square. And in the denominator of the dispersion relation, we have the energies of the particle holes, all the particle holes we are summing, and the energy we want to calculate. And this is equal, this must be equal for the consistent situation to the integral of the deformation of the density and the deformation of the potential. Well, surely not all the details can be understood here. But I wanted to write down the expression because this expression contains elements that later we will find are identical to the RPA. So it's enormously surprising, or that a so semi-classical description can, in a way, be identical to RPA, but not to any RPA, because in RPA you have to produce a residual interaction, and it depends on the model that you use to produce RPA. So, of course, it's identical in some sense, but in a sense that is very general. If not identical, approximately identical to RPA. In particular, it's identical in RPA if the residual interaction is parametrized in a very simple form, which is this one. which is called the separable interaction. If you have a separable interaction, which is, remember, the residual interaction has to be a two-body interaction, but if this two-body interaction can be written down as the product of a function in one of the particles and a function of the other particle, is called a separable force. And well, it's a special way of writing down the residual interaction. And this coupling parameter is the one appearing here. And this parameter appearing in the separable term is precisely this one. Well, you could say, well, that is a very special case of RPA. Yeah, but many forces can be formulated, at least in an approximate way, as a separable force. So in many senses, the description of oscillations in a semi-classical way encounters the results of RPA. And well, this is a nice feature that particularly myself have used for simplifying many calculations.
This is a result of solving
The perturbation theory stuff.
that perturbation right there.
This is the result. So the energies that fit the self-consistent equation, I mean that the final density agrees with the classical density fluctuation, happens only for special values of the frequency that are given by this equation here.
And this B residual comes from this in what way?
No, this is the result coming from all the semi-classical stuff. But as I was saying, you can recover exactly this result if you go back to the microscopic RPA method that I was showing before. Okay, and it coincides as far as you use this kind of residual interaction. So it's a special form for the residual interaction. I was saying it looks somewhat special, but in fact many different forces, microscopic forces, can be rewritten in this way. There are many papers where we can look at this. But as I was saying, this is the correspondence between the classical microscopic or semi-classical and microscopic descriptions. I will use both of them depending on the situation, depending on the kind of calculation we want to do, and then we will discuss when one is the best, when we have to be careful. Well, this is the stuff that will be discussed in the next lesson. Now I think that I went too far in time, and now I think. Pardon me? Mm-hmm.
Let's say 5 to
Really?
10, so we stop there for 15 minutes or something like that. It's very a more substantial break. No? So I think it's better if you
Well, it's a proposal.
I think because otherwise you make a break. Now then you have only 20 minutes to go.
Okay. Well, good. Well, so we had until now 2 or 3 methods for calculating the frequencies of excitation of a even nucleus, even nucleus, and this lead to some energies. In this case, coming from the self-consistency condition. In the other case, coming from the diagonalization of an eigenvalue problem in the Tandankov or in the RPA. Well, one aspect of this later method I have shown you is that it's based on the harmonic oscillator. The harmonic oscillator, we said that the dynamic degree of freedom, which was the quadrupole deformation, was having some 0-point motion that now we know how to construct because we know the energies. We still don't know the harmonic oscillator coupling constant, but okay. Well, a consequence of the harmonic oscillator hypothesis is that you can have an excited state 2+ if you act with the rising operator. Then you can go to the two phonon states, namely the state having two quanta of the harmonic oscillator. So we would have the 2+ square state. When you have a 2+ square, what you have are two vibrational states, and here you can have different possibilities of coupling the two quanta. The two quadrupole quanta can couple to 4, 2, or 0 angular momentum. And if you continue with the harmonic hypothesis, you go to a third level in energy. All of them have the same energy interval. So this is 2 h bar omega, and this is again h bar omega. So this is 3 h bar omega, where h bar omega is the quadrupole basic oscillator energy. In this case, you should go, I don't remember exactly, but it's something from 6, of course, to 0, or to 2, I think. Well, I don't really remember exactly. Okay, anyway, there are different possibilities of angular momenta, all of them with positive parity. So we can generate a spectra. This would be the quadrupole spectra. Of course, in the same nucleus, for example, calcium 40 or calcium 48, we can generate the octupole spectra. So we have something similar. Maybe the energy is different, or surely the energy is different. And here you have, which gives 3 from 6 to 0. Okay. Maybe the hexadecapole or the lambda equal to 5. Lambda equal to 5 is sometimes also an important with the method I'm showing you. But okay, this can continue to any multipolarity that you consider a good candidate for generating the spectra. And in this way you generate a spectra, of course, of the nucleus. Well, taking into account that these are degenerate, in this case a triplet, in this case a quadruplet, in this case a quadruplet. Well, if you go to experimental data, there are some nuclei showing this structure. Of course, the pure harmonic hypothesis breaks a little bit. So if you go to real spectra, you will find that these three states are somewhat close together in energy, but with some kind of breaking of the degeneracy. And even more if you go to higher energies. But still you can be, let's say, happy because you have a first description of the system. And the same, of course, happens if you go to octupole or to any other multipolarity. Well, so the harmonic oscillator hypothesis works, we can say, works as a first order approximation. Well, what is RPA saying about all this? Because, well, RPA is saying something similar to why? Because RPA is not based on harmonic oscillator hypothesis, it's based on the contrary, on fermion excitations. Remember that the operator, Tandankov, if we want to be easier, in Tandankov, the operator generating the excited state is constructed with fermions. Well, where is the harmonic oscillator hypothesis coming, or can it be interpreted in terms of the Tandankov? Well, in terms of the collectivity or the coherence. So I was saying you before, if coherence, we will have large electric transitions, amplitudes. Remember the expression was the Tandankov and the basic single particle contribution. And one must remember, I have not said, but it was kind of implicit talk you of Tandankov, that all these states must be normalized. Okay, I didn't say that before, but you can easily figure out that when you solve the eigenvalue problem and you sum all the components of your eigenvalue, you have a normalization condition. Okay. Well, I was saying that in order to get a large value of the quadrupole intensity for the phonon, you have to have coherence. But another aspect that contributes very much, and it happens in the low line, to the large values of the quadrupole amplitude is the fact that there are many components. So if you have that show coherence, large values of M. The need of coherence is obvious because you have to sum things with the same sign. Why should we impose the condition of many components? Well, it has to do with normalization. Suppose that you would have only one component. If you have only one component, I mean a particle hole that by some reason is giving you a physical state because it's not coupled for some reason. It's just an example. Well, in this case, you would have only a component, and you would have the only, if you have only one, in a situation of only one, you would have only one component, and the sum, of course, would be coherent because you only have one element in the summation. small, or at least smaller than if you think in having two particle holes contributing. Imagine that you have two particle holes contributing. Then, and say they are more or less the same amplitude. So imagine that instead of only one, you have two. And this is, in this case, if they have to be normalized, this is 1 over square root of 2, and the other also. And you go now to the quadrupole intensity. You have two contributions. Okay? And remember that the BE2 is the square of this number. So in this case, if you make the counts, which are rather easy, you obtain here 1/2 of M1 plus M2 square. Suppose that M1 is similar to M2. So you see here that now, when you square, because this has to be a square, you obtain 2 times M. So it's a double than if you had only one particle. So in the end, what you can see that if you have a large number, let's say N elements here, of course, many more, normalized properly, in the end, I'm doing a very rough approximation that all of the matrix elements are similar, you obtain an enhancement of the transition that is proportional to the number of components. So if you have many components and all of them are coherent, then you obtain a strong electric transition. Okay. Okay. Well, but I was talking about the harmonic oscillator hypothesis. Well, the harmonicity of the RPA comes from this fact.
I'm sorry. So you're saying that if there's many particles
Is that contributing?
then you will have a larger transition.
Exactly. Exactly. So collectivity,
Throwing in
the
the structure.
structure where?
That's where the structure comes from, based on the number of particle states throughout, right?
The structure.
Of the cross section.
Okay, yeah, if you think in, yeah, I'm talking all the time about the electric transitions, but this also can be applied to inelastic scattering, because instead of the electric field, you have the external nucleus field acting on the nucleus, okay, which is another single particle. But let us concentrate on the electric one. Okay, so as I was saying, if you have a large number of components, then harmonicity comes as a consequence. Suppose you have many transitions from below the Fermi energy to above. You have many different. And this is the structure of one phonon. Let's say this is the wavy line number 1, or the 2 plus. Now, if you superimpose another 2 plus, well, you could say we are going to have difficulties, because if now I want to superimpose to this structure another similar structure, I will find that sometimes this level is occupied, or this hole is not available because it's already used by the first quadruple vibration. Well, this is right. I will have some kind of Pauli inconveniences because I cannot use again particles that were used to for this. But remember that all these transitions are not simultaneous. They are in a linear combination. Sometimes you can find the nucleus doing like this. Then after some time you can find it doing like this. So they are not all simultaneous. On the contrary, they are a superposition, a linear superposition. They are not direct product, but it's a summation. So if I now come, this would be the first 2 plus, okay? If now I come with a second 2 plus, or I want to construct a second 2 plus on top of this, well, I could have some difficulties because, well, sometimes, as I was saying, I will have this jump already active in the first phonon and I will not be able to use it for the second. But if the number of components is large enough, the probability that this occurs, it will be less and less. So for very collective states where n is large, I will have little difficulty in superimposing 2 similar excitations because I will have very little probability of interfering. Of course, some interference will occur, and this is the reason of this break of the pure harmonic structure of the levels when you superimpose different phonons. So Pauli principle is one of the reasons, not the only one, but one of the reasons why we find this break of the pure harmonic situation. But at the same time, it explains why in a pure fermionic description, where harmonic oscillations are not something a priori, it happens, and is due to the large number of components we have in a very collective state. Okay. Well, in the first lesson, I was supposed to talk about also the odd system. So far, we have talked only about the even system. But I think that maybe, well, let me sketch what will be the odd system lesson that obviously will be tomorrow. And in this way, well, if you read the notes, you can somewhat prepare the lesson for tomorrow. And the idea when we go to the A+1 system, to the A+1, is that on top of the reference system that I was saying before, in the example of calcium, of carbon 12, on top of this reference state or reference system, we add a new particle, for example, a new neutron. This was the neutron side, and this was the proton side. Okay. Well, in the A+1 system, we have several possibilities for generating the spectra. We have the possibility, of course, of doing the phonons of the original A system, because it's still there. So we will have the possibility of phonon, but in presence of a neutron. So our states will be now represented diagrammatically in this way. So we will have particle, and if we have any phonon excitation of the, say, core, we will represent the state in this way. Of course, not necessarily the core must be excited. We could have the core in the ground state and the particle. Well, the ground state, I will not write it down. So when I write nothing, is ground state. And the particle, well, the particle can be in several of the levels available to the neutrons, or if protons, if we were in the case of a odd proton. So we will have states of this kind, where the particle can be in different levels, or states of this kind, where we have also, apart from the particle in some orbital, some kind of phonon or excitation of the core. So going to the A+1 system, we have to deal with this more rich set of possible states, and we will try to, well, to diagonalize the residual interaction appearing also in this. A lot of residual interaction is already, and this is very important, a lot of residual interaction is already inside our model because we have solved the core excitation using the residual interaction in Tandanko or RPA. But still, some new residual interaction effects will appear when the new particle is present. Okay? And, well, this will have an effect on the energies. So the energies of the particles will not be exactly the ones that we obtain with the spherical potential, solving the Schrödinger equation. We will have some modification, okay? Some, and this modification is what will be called the self-energy. So there will be some modification to the energies of the particles. And also will be some modification to the particle phonon configurations. In principle, in a phonon configuration, the energy would be just the sum of the particle and phonon energies. But, as we will see, this will be modified also. Just let me note that if you have a J prime particle and a lambda pi proton, phonon, sorry, here you have many different coupling possibilities, because the coupling, the total angular momentum, can go from J prime minus lambda to J prime plus lambda. Okay? In principle, all of them having this energy, but it's a very initial energy value. As I told you, the interaction, the residual interaction, will modify this energy, and this modification will depend on, among other things, will depend on the coupling of the total angular momentum of the two elements, the particle and the phonon. So that this degenerate multiplet generate will get some splitting due to residual interaction. Well, this splitting of the multiple degenerate multiplets and the self-energy, that is the modification of the energy of the particle, will be the subject of the next lesson. Okay? And, well, with this we get some delay, but as I told you, I think that then we can rush, because the basic concepts will be then repeated in the end, and it's better just to see them in the beginning with some detail. Okay? Well, I went too far in time, but